arrays of often hundreds of different samples. So here's sort of a concept, okay? This is a single particle. I'll tell you a little more about it. And it's in a transparent plastic. And then what we do is we use a pulse laser to shoot this flyer plate or metal disc at it at high speed. And then we look up from the bottom and see what happened. This is kind of a block outline. There's a microscope, and you use the laser to shoot the pulse, the flyer plate. And then we have a bunch of diagnostic instruments. And today, let's see, I think I'll be talking about not the femtosecond laser, nanosecond laser, a flash lamp just to make light, an optical pyrometer that measures emission spectra and temperatures, and a high-speed camera. Okay, so this is the secret thing. Actually, the story is I was working on a MIRI project for the Army, and at the end, I don't know how this worked, but the program officer called us up and said, "Oh, you guys did a good job. We're going to give you $1 million. Go ahead and give everybody a piece." And I went, "Oh yeah, okay." So I'm going to build a laser flyer plate. And the big problem with flyer plates when you launch them with a pulse laser is uniformity of the laser beam. If one part of the laser beam is more intense than another, what'll happen is half the flyer plate will go at one speed and the other half will go at the other speed. And so I looked at all these technologies. Boy, was I lucky when I found this one from France, from a company called Cilios. Okay, and so the way it works is that there's a big disc with 1 million tiny little diffraction gratings on it. And each grating has the property that it's a tiny thing. If you uniformly illuminate it, it produces a uniform disc in the far field. And then what you can do is you can superimpose 1 million of these. And what's really important is with pulse lasers, usually the shape of the beam changes during the pulse. So it starts out maybe small and then kind of blooms. And what happens is sort of no matter what shape this beam is at any instant in time, each one of these tiny things will see essentially uniform illumination. And so that's how we can get a very uniform beam in the far field and launch really nice flyer plates. Oh, I have 2 labs. Here's what the older one looks like. You stand here, and here's the big pulse laser, and it goes, it shoots down onto this microscope. We like it to shoot down for a number of reasons, but one big one is that if you've got a liquid, if you turn it like that, it falls out. And then there are all kinds of diagnostics. This is the velocimeter, fiber optic velocimeter that measures material and flyer velocities. This is a femtosecond laser I don't use much anymore. This is the pyrometer, which is also on the floor because it's coupled electrically and optically. And here's a high-speed camera over here. This is a little plot I made a few years ago. If you just want to know what you can do with flyer. Grief, what's this? Okay, I don't know. It's news to me. If you want to just launch flyer plates, then this is the laser we're using is a YAG laser that makes 2.5 joules. So the laser gives you an energy budget, and you can spend it in different ways. You can spend it in velocity or mass. And when I say mass, that can be the diameter of the flyer plate or the thickness of the flyer plate. So the kinetic energy is proportional to the mass, but the square of the velocity, okay? And so you get these sort of square root curves, which means, yes, it is harder to make higher velocity because you can see it sort of topping off. But this is a very thin aluminum flyer plate, and it goes 6 kilometers a second. And this is the one that we use almost all the time. It's 4 kilometers per second. It's 25 micron aluminum, which coincidentally is the Reynolds wrap in your kitchen. Although for some reason my students spent $100 on expensive Reynolds wrap. And then this is this is copper and so on. And you can really launch all kinds of things, plastics, metals, and so forth. This is just a reproducibility chart, okay? So this is the velocity reproducibility, which is good to about 2%. And this is the arrival time reproducibility. If you're going to do spectroscopy, you really want to know when the flyer plate is going to hit the sample. And all this variance here is just due to the fact that the velocity is a little different. And so the flyer plate arrives at different times. I'm going to cut out of this for a second and see if there's any way to make this stupid thing go away. Oh, goodness. Okay, I don't know. We're going to live with it. Oops, don't want that either. Well, that's a new thing to add to my list of crazy things that happen during talks. Okay, here's one example of an array. This is an array of 200 tiny plastic explosives. So a plastic explosive is a powder, often an organic material, and sometimes metal powders and inorganic powders with a little bit of glue. And these are nano X-ray CT scans of two of these. This one's made from a material TATB that's real hard to control the crystals, so they're pretty grainy. And this one's made of PETN, which is very easy to use. And I think you can see that, the rings are from the X-rays, right? There's one big crystal here, and there's a tiny void here, and there are more voids here, okay? So a plastic explosive, I didn't mention it's powder, glue, and sometimes voids. But with something like this, you can blow up 200 of them in an afternoon. And the mass of each one of these is 100 micrograms. So these experiments are intrinsically safe, which is nice. Okay, so this is the output from our pyrometer. The pyrometer measures the emission spectrum in the visible range. It's 450 to 825 nanometers. And it takes a spectrum every 0.8 nanoseconds. And so in 100 nanoseconds, you're getting 200,000 spectra. And you don't want to necessarily show all of them, so you can average them in some way. The shape of the spectrum gives you the temperature. Okay, so if you have an electric stove, you turn it on, and then as it heats up, it becomes red and then maybe yellow. And then the sun is yellow because its surface temperature is 5,600 Kelvin. It also measures the intensity of what comes out, and that's called the radiance, and it's got units. And one nice thing is that we calibrate this radiance. So if I put in a sample one day and then a month later I put in a different sample, I can compare them quantitatively. All right, so this is a plastic explosive made from HMX, which is, I believe, the highest performance explosive that's used in the US. There's a slightly better one called CL20, but it's not in wide use. This is the time-dependent profile here. So let's see. Let's first look at the radiance. Okay, so the radiance is the thermal emission being produced, and it's an approximate measure of how much energy is coming out at any one time. Okay, and what we're seeing here are two peaks. All right, this is a nanosecond peak here. It's set around 10 nanoseconds, and this is a microsecond peak. It's around 3. And the area of this peak is much, much bigger than the area here, right? Because it's, height, pace times height, and it's a log time scale. And we associate this first peak with ignition. That is, when you shock the material, you form what's called hotspots. And the reason for this is that it's a highly inhomogeneous material, and there are microstructural features where the shock energy gets concentrated. Hotspots play the role of, if you're going to light a fire, you take a match and maybe you light it. If you just put the same amount of energy in uniformly throughout the whole fire, it wouldn't ignite. But if you have a hotspot, it'll ignite. Okay, and then you make lots of hotspots, and the really tiny ones cool off very quickly, and so they go down. But then you're left with so-called critical hotspots. These are ones that are big enough to grow, and then you get this growth process. When you look at the temperature, initially the temperature is ridiculous. It's 5,000. I've seen 7,000. And we've explained that has nothing to do with chemistry, okay? In those little voids, there's air or other gases. And when you compress a gas, the volume changes a lot and the temperature goes up. When it gets down here into the 4,000s, that's when you're sure that it's HMX chemistry. And then these are the hot spots. And like I said, a lot of them cool down. And then what you're doing here is called deflagration. Deflagration is a fast burning process where the fuel and oxidizer are already mixed. Okay, so HMX contains nitro groups and carbon, and so you can create carbon dioxide and water, for instance, but you don't have to move oxygen into the carbon. It's on the same molecule. All right, so one of the problems is that there's plenty written about what happens inside a plastic bonded explosive, but there's basically nothing on seeing it. Although these days with new X-ray sources, we're beginning to see better inside the explosive. But one day I had an epiphany and I went, okay, I know, here's the problem, okay? A plastic explosive looks like toothpaste. Well, yeah, looks like toothpaste. Toothpaste is a powder that has a gel, right? So there's a binder and a powder, and you really can't see inside of it. So if you put a shock wave down here, if you impact it, there'll be a shock wave, and there'll be a lot of light coming from the shock front, and there'll be light from the reaction back here because it's at such a high temperature. But by the time it gets to you, it's just a big mess. And so I went, oh, I know. Let's just make a plastic explosive that's one little tiny crystal thick. And we'll embed it in clear plastic, and then we'll shock it. And then we can just sit here and watch it as the shock wave goes by. And this work was done by my postdoc, Donna. These are what some little HMX crystals look like. This is what a plastic explosive, this is what a tiny part of the plastic explosive wafer looks like. The really bright spots are where crystals happen to be pointed straight at you. And then this is an algorithm that allows you to identify the crystals. So I can actually count how many HMX crystals are in here. This is binder. And I can watch what every crystal is doing during the shock passing through. So now I'm going to show you a movie. This is a movie of that stuff I just told you about, the HMX plastic bonded wafer. And the bright spots are the thermal emission. So this one here is not spectrally resolved. We're just seeing all the thermal emission. But the brighter it is, the more chemistry is going on and the hotter it is. And you can sure see the hot spots here. Let's see, here they are. You can see the hot spots. And then you can see this hot spot's growing. And then it's cooling down. Remember, I showed you initially it was 6,000 or 7,000 degrees. And now it's cooling down. And then as time goes by, eventually, basically everything is burning. Okay, so people have been talking about hotspots since 1900, but really haven't seen them in real time. So here they are. And then this is a project where we're trying to figure out what causes the ignition. And so in this graph, these little white lines are telling you where the crystals are. And then the red thing is telling you where the reaction is happening, where it's thousands of degrees. And here's a big, beautiful hotspot. And then you can see fuzzy, it's spreading out. And there's another one up here. And so what this does is, this is a way of doing chemical kinetics in a problem where the reaction is moving in time and space, and it's very fast and very violent. So I had this great idea that we would do machine learning on this, and we would try to figure out which configurations give you hotspots. And it was kind of a dud. And I think the reason it was kind of a dud is that under the microscope, we have resolution of about 3 microns. And a lot of these things, tiny voids and stuff, are hard to see. So there's no obvious reason why this is a hotspot, okay? But if I had to tell you, it looks like the hotspots are generally associated with big crystals. Okay, now here's my current fascination, and that's growth. All right, so once you have a hotspot, the reaction grows. Okay, so ignition is very important for explosive safety, right? Once the thing, you want to avoid them igniting, because then a bad thing can happen if you're in the neighborhood. And of course, the classic is the aircraft carrier Enterprise. Some guy with a crane dropped an atom bomb on the deck, and the explosive, the nuclear stuff won't go off, but the explosive went off, and it was a big mess, and it cost a real lot of money. And then ships, the Navy cares about this a lot because sailors sleep with bombs. All right, but the growth is very important if you want to try and design energetic material devices. Okay, so for instance, there's this thing called a shape charge where you use 2 explosives and they channel the energy into a jet. One of the things that we want to try and do nowadays is control detonations and make them do specific things. And so like you can put tungsten balls into an explosive, and when the detonation hits it, it may stop briefly and then reform. And you can use that to control various things. But this reforming is all the growth rate, so that's really important. So let's see, where am I? Oh yeah. So what I want to do is use machine learning to predict, if I know this, if I know where the ignition sites are, how's the growth going to occur? And this is where we're at, which is not very far. So here's a picture of hotspots in plastic explosive, like I was showing you. And then my postdoc Donna picked 7 of them for some reason, these 7 here. And then what we did is we looked at the autocorrelation function of the 7. And you can see that they're decaying because they start out hot and cool down. And this one, these two seem different from the others. And in fact, this one's going up. Okay, what we need to do now, and I think my undergrad Ryan is on. Yeah, there he is. Ryan Eisenstadt is in the audience. Is that now we're trying to do cross correlation, okay? Because the simplest model for these hotspots is that it's just thermal diffusion out of the hotspot into the reactive surroundings. But you know, it's not a hotspot. It's a little bomb. It's a little explosion. And so what I want to look for are highly non-equilibrium, long distance travel. Okay, so if this guy blows up, then I want to see the correlation between this and this. And so I have a collaborator who does machine learning, and I talked to him and he goes, well, I referee a lot of papers. If you have 10 data sets, I reject you. If you have 100, I say it's a chance. If you have 1,000, I say it's pretty good. And if you have 10,000, I say bingo. All right, and so Donna is busy trying to make hundreds of these so that we can use machine learning on them. Okay, so I think I'm going to move to the next topic, which is more powerful explosives. So the first the first explosives were gunpowder, and gunpowder is a low explosive. This means that if you have a pile of gunpowder and you light it, nothing happens. It just fizzles. But a high explosive is one where a shock wave runs through it at hypersonic velocities, causing the chemical reaction. So nitro, what is it? Uh-oh, I'm blanking out here. Anyway, liquid nitro compounds, which are very unstable, were invented. And they were explosive. And Nobel got the idea of stabilizing it using kitty litter, vermiculite, and that was TNT. So TNT has an energy, a heat detonation of 7 kilojoules per cubic centimeter. And then in 1950, we invented RDX, which was better. And in 1960s, we invented HMX, which is 11. And this super CL20 stuff I was talking about is 12. But you can see that we haven't even doubled things in the last 120 years. So it looks like organic explosives like TNT and HMX and CL20 have sort of hit a ceiling. But we're always interested in better and more powerful explosives. And so if you go look at the Handbook of Chemistry and Physics, what you find is that possibly the most energetic reactions are where you burn metal. And I wouldn't be surprised, Steve, in your freshman chemistry class, if you didn't burn a magnesium ribbon. That's really impressive. But it burns really slowly. Okay, and the reason it burns slowly is that it's all fuel, and you need to have the oxygen in the air diffuse over to the thing, and that's slow. These things are fast because the oxygen's on the same molecule. All right, but here's 2 candidates here. Aluminum Teflon is used now in a number of explosives. And this is a ceramic oxidizer, molybdenum. It has 3 oxygens. And you can see here that compared to even the best 12, that this one's 16 and this one's 21. And boron, which is problematic for a number of reasons, is 24. So there's the potential of doubling the energy, which is really great. And you'll recall E equals 1/2 mv squared. You'll recall that that could mean 4 times the detonation velocity. All right, so everywhere people are taking explosives like HMX and adding aluminum powder. And what happens is you get increased total energy output, but you don't get a more powerful explosive. In other words, the pressure and the velocity doesn't go up. And here's the explanation, okay? So this is one of the simplest theories. This is the second. There's a very simple one, and then this is the next most simple. It's called the Zeldovich von Neumann-Düring model. And it says that the detonation is a shock wave that is moving at high speed. In HMX, it can be 9 kilometers a second. And when it hits the unreacted material, it causes to react and release energy. And then this huge high pressure front where it's releasing energy expands. And if you have a reaction here, the energy from that reaction can move through this dense material at high speed and add to the shock front. But as the material expands more and more and more, eventually you get to a point where the speed of sound in this material is equal to this detonation velocity. And that means that if there's an energy producing reaction back here, it doesn't have time to make it to the shock front. Okay, when you throw aluminum powder into an explosive, what happens is it reacts slowly, and I'll tell you why in a minute. Okay, but it reacts behind this thing called the CJ or sonic plane, and it can give you additional energy. Let's see, it reacts with some of the products from the detonation, like CO2 and water, but it also can react with air, and that's typically called afterburn. All right, so when I add aluminum, I get more energy totally, but I don't get more pressure. And so what we're trying to do is we're trying to figure out how to force aluminum or other metals into reaction so fast that they'll react between this shock front and the CJ plane. It's called the reaction zone. So if I had this stuff, which I'll tell you what I'm doing, then we can have a more powerful explosive. How fast does it have to react? Well, it's a bit of a question because it's really hard to find. It's easy to find the shock front, okay? You watch the explosive and oh, there it is. But it's really hard to find the place where the speed of sound becomes some particular value. So there are some issues, but I would say based on my literature reading that it should take about 20 or 30 nanoseconds. So what I'm telling you is I want to try and make aluminum make more energy than HMX in 20 or 30 nanoseconds. Okay, here's why aluminum reacts slowly. This is a quarter of a sphere of aluminum in a molecular atom molecular dynamics simulation by my friend Priya Vashishta. This is the first one ever done in 2007. And what happens is when HMX and TNT react, they tend to make small molecules like CO2 and nitrogen and H2O and just a mess of other things like NO and N2O and so on. But when aluminum reacts, it makes alumina, or which is when in crystalline form, it's sapphire, and that's Al2O3. And it's that lattice energy, it makes huge amounts of energy. Okay, but it's a condensed phase material. So when you react HMX, you can shoot millions of little molecules out of the back, and that increases the entropy, and the free energy change gets really big. But here what I'm trying to do is I'm trying to force it to take the reaction products and condense them into a condensed phase. Okay, so in this simulation, the large particles are oxygen. These are aluminum. This is, like I said, a piece of aluminum crystal. Oxygen from the air comes and it lands on the surface, and it produces a little bit of this alumina, an alumina shell, which is semi-porous. And then what the oxygen has to do is it has to diffuse over here, and it has to diffuse through the shell to get to the aluminum. And to extract all the energy from this particle, what you have to do is you have to make this aluminum shell grow inward until it's taken the whole particle. Okay. In the best conditions, like if that's a nanoparticle and you have lots of oxidizer, that takes microseconds. But often it takes milliseconds. And I already told you the goal here is to make it happen in 10, 20, 30 nanoseconds. All right, so what we did is we turned to a new processing method many of you heard about. I believe Zach's here, he knows a lot about it. It's called ball milling. All right, and so what you do is you put some materials in here. And in this case, a fuel and an oxidizer and maybe some other stuff. And a lot of times there's an inert fluid. We're using hexanes typically. And the purpose of the fluid is to help mixing, but also these are explosives. They start to react, it'll carry the heat away and it saves you. And then there's stainless steel balls in here. And what you do is like a washing machine. It just rolls around and the balls go bam, 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 and they pound this stuff to death. And here is a resulting piece of stuff. This was an aluminum. This was a mixture of aluminum and copper oxide, copper oxide, which is the oxidizer. And aluminum, as you probably know, is soft. And copper oxide is a ceramic. And so what these balls do is they pound the copper oxide into nanodust, and they smash it into the aluminum and fold it over and over and over again. And what you end up with are these microparticles. Here's an 8-micron particle. And the bright stuff is the oxidizer, and the darker stuff is the aluminum. And I'll show you in a minute. What you can't see is if you look in here, the bright particles are everywhere. I like to think of this as an oatmeal raisin cookie. Okay, the aluminum is the soft cookie, chewy cookie, and the little particles are the raisins. The oxidizers are the raisins. But what you have here is you have a microparticle, but it's shot through and through with oxidizer nanoparticles. In our most recent experiment that we're getting almost ready to publish, we made 2 batches of this stuff. In one batch, we put a small number of steel balls in, and in the other batch, we put a lot in. And so as you roll this thing around over and over again, you don't get as much mixing in the one with the low ball to particle ratio. So these are electron micrographs of the microparticles in the poorly mixed ones and in the really well mixed ones. And then my brilliant postdoc, Shiva Valuri, figured out how to slice these microparticles with it was tricky. But so these are cross sections of these particles. And again, if you look at the cross section, the bright stuff is the oxidizer copper oxide. The gray stuff is aluminum. The black stuff is voids. And in the well mixed one, the white particles are generally smaller. They're on average about 8 times smaller in volume than they are over here. And you have fewer voids. Okay, so to make aluminum react with copper oxide, you have to mix the fuel and oxidizer. And so conventional wisdom would be, oh, this well-mixed thing should react a lot faster than the poorly mixed one. And that's certainly what I thought for a moment. But here are the results. Okay, so what we do is we take single particles and embed them in transparent polymer and shock them. And then we do that 100 times or so. And each time we do it, we get a temperature history. And this is the radiance, the emission history. And this is the poorly mixed one, the red one, and the well-mixed one is the black one. And you can see this well-mixed one is practically inert, whereas the poorly mixed one gets really, really hot. I mean, here, some of these the shaded region is the variance. Okay, this is because we looked at lots of different particles. Some of these particles are 7,000 degrees, and that's very brief, but some of them are sitting here reacting at 5,000 degrees, whereas HMX reacts at 3,300. All right, so what we have here is we have a material which, when shocked, produces much higher this is where HMX would be. It produces much higher temperatures than HMX, and it produces those temperatures on the 10 nanosecond time scale. And if that was it, I'd be busy filing patents. But unfortunately, if you look at the radiance on a longer time scale, this is what you're seeing here. Okay, but most of the light is coming out here in microseconds. All right, so only a small fraction of this material is coming out fast. What's happening is we don't have the optimum size oxidizers and the optimum distribution of oxidizers. And most importantly, we don't have enough oxidizers. Okay, in this process that we're doing here, I told you it was like an oatmeal raisin cookie. Well, you can't make an oatmeal raisin cookie out of only raisins. Okay, you got to have some aluminum to hold this thing together. And so it turns out these particles have 4 times too much aluminum. So what we're going to do, what we've done is we've shown that there's a geometry. Okay, and the geometry is you really want the oxidizer inside. And you want a specific size oxidizer particle, which is relatively larger than nothing. Okay, and then what happens is these particles react. And remember, the trick is that you're not trying to make jets of gas. You're trying to make solid alumina, or liquid alumina in this case. Okay, but by having the reaction trapped, you trap all the little molecules that get produced and allow them to condense. Right, so this one I am writing a patent on. The key is then that if you really want to make aluminum react super fast with high energy, you need this proper geometry. All right, so let's move to another topic. Oh, good. I'm doing good, which is damage. All right, so when you shoot a flyer plate at something, bad thing can happen. One day I came into the lab and my students had a little green toy soldier and they sat him down and they were shooting flyer plates at him. And I really didn't know what to expect, but that tiny little flyer plate, which is 0.5 millimeter in diameter, knocked this guy on his butt repeatedly. So you can create a lot of damage. And one place where that's important is outer space. All right, if there's a micrometeorite, or these days there's just huge amounts of debris in low Earth orbit because we launched all these satellites in the old days and nobody bothered to clean up after them. And so it's very important to have materials for space travel that are resistant to meteorites. In low Earth orbit, the other problem is space weather. All right, so you may remember from your chemistry that Earth's atmosphere density is 1 atmosphere down here, which is good. But as you go higher and higher, it declines exponentially. And in low Earth orbit, it's pretty low. It's around 10 to the minus 5, I think. But in low Earth orbit, your satellite is moving at 12,000 miles an hour, or 8 kilometers a second. And when it hits air molecules like O2 and N2, they dissociate. And so any material in low Earth orbit is constantly being bombarded by hypervelocity oxygen atoms and nitrogen atoms and who knows what else. Okay, so my collaborators here, there's a big group of people who did this, but Nancy Sotos is a materials chemist, and Yannis Chasiotis is an aerospace engineer, and these are the students, and this is the student who worked in my lab. Nancy has proposed, and I think she's right, that there's this material called the PDCPD. It's a thermoset polymer. It's extremely dense, which helps resist damage, and you can fortify it with silica nanoparticles. And so what she did is she sent samples of this DCPD polymer up to the space station, and they sat there in low Earth orbit. Some astronaut goes out there and puts them outside in the space weather, if you will, and they orbit the Earth 1,000,000 times, being continuously bombarded by oxygen atoms and nitrogen atoms. And then, cross your fingers, they went out and got it and brought it home, and we got it. And this is what it looks like using high resolution microscopy after 1 year in space. And it started out being a perfect smooth thing, but now it's a bunch of stalactites. And one of the things about damage is that once you have a kernel of damage, it grows. Okay. So anyway, this is a characterization, but then what we wanted to do is we wanted to know, what did that do to meteorite resistance? And so the students took all this stuff over to our materials research lab, where they have a lot of instrumentation, and made these measurements and looked at the dangling bonds and the atoms and all that stuff. And then it was done, they gave it to us, and we shot flyer plates at it to pretend meteorite. And this is what it looks like after a flyer plate hits it. Now we're gearing up to do more of this, because Nancy and Yannis have figured out how to do this space weathering on the ground using a plasma reactor. But there's a lot more you can do, and I'll show you that. But the bottom line, I was a little disappointed, is the meteorite resistance didn't seem any different before and after the weathering. So let's move on to more damage. Okay. One of the things that we can do, haven't seen much of it, is real-time studies of the impact. Okay, now, if you are moving at Mach 12, which is 4 kilometers a second, you're moving at a velocity of 4 microns per nanosecond. And so if you want to look at 100 micron crack forming, that's going to take 25 nanoseconds, all right? So real-time damage from high velocity impacts is happening in nanoseconds. And what you're seeing here is, this is a piece of glass that we hit with a flyer plate, and you can see all kinds of stuff spraying around and damage. But this is what it looks like in real time. Here's the first 10 microseconds. I'll tell you what you're seeing. You're seeing so-called triboluminescence. Okay. If you take a brittle material like glass and you suddenly crack it, you form a crack. And due to statistics, there's always going to be more electrons on one side than on the other side. And so you get a big electric field. And I mean big, it can be 10,000 volts. And so what will happen is the electrons who see this big field will be accelerated, and they'll smash into the other side and make light. You can do this at home in the winter, right? Just rub your feet on the carpet, and you'll have unequal number of electrons on the carpet and on your feet. And then when you go touch the doorknob, you get a big spark. All right, so that's what you're seeing. And you can see here this is where the flyer plate hits, and here's where the damage is spreading out. Okay, and so on. And then this is the velocity of the flyer plate. The flyer plate's going 4 kilometers a second. Yeah, there's nanoseconds, okay? And then when it hits, the velocity slows down very suddenly because this is a very beautiful flyer plate and hitting a flat piece of glass. Okay, and then what happens is glass starts to move because that's what a shock wave is. It's where you make the material move at high speed, and then you can see the rest of the response. Okay, so let's see. I had one more thing I wanted to talk about, hypersonics. So we've been shooting flyer plates for a long time. We always shoot them in vacuum. And the reason I shoot them in vacuum is that when you shoot them in air, the air gets hot and it makes a lot of light. And if you're trying to do spectroscopy, all you see is hot air. And then some of my students will go, well, there's even more hot air coming from Professor Dlott than from the flyer plate. But one day, some professors from the Aero and Astro department came over to talk to me about a proposal. And I went, oh my gosh, these flyer plates are tiny hypersonic missiles, and there's a lot of money for that, and people like it. And so maybe I ought to think more about that. Okay, and I'll tell you what we're doing, which is pretty new and hasn't gotten as far as I'd like. Okay, here's a hypersonic missile. Let's see, what's a hypersonic missile? It's a definition, but maybe Mach 3 to Mach 12 is one definition that people use. That's 1 to 4 kilometers a second. Oh, Mach 1 is 0.33 kilometers a second. Okay, so 1 kilometer a second is Mach 3, and so on. And then if you have a hypersonic missile coming through the atmosphere, you're going to get a bow shock, which is what this is. This is a shock in the air. And you're going to get air dissociation. And you're going to get, like the space weathering, you're going to get high energy molecules hitting the surface. Your problem is that these missiles have a window on them, usually with sensors behind them. And the weather, the atmosphere is not too bad for a missile, but in the air there is raindrops, hail, ice, and dust. And if you're a laboratory chemist, then raindrops are water and dust is silica. And so what you're interested in is what happens when your window or your other material hits a raindrop or a dust particle. And it's not a simple problem because the particle has to first interact with all this air. By the way, this is the stuff that makes the sonic boom is back here. It's where all this, there's a vacuum, well, there's a partial vacuum back here. And when the air comes back here and it collides, you get that big noise. Okay. And so what's interesting is to find out at the molecular level, what happens to materials like this glass that you saw got hit by this piece of aluminum? What happens to them? But one of the problems is you don't know what's hitting them because first they got hit by this big burst of wind. All right, so what we did is we went, okay, let's let air into the machine so that we can watch the flyer plate or tiny hypersonic missile interact with the air. And my student, Shivashri Gowda, started doing simulations of that. So she took a 0.5 millimeter flyer plate, and these are high speed. These are 4 kilometer per second flyer plates moving to the left. And then this is air. This is undisturbed air, and this is the air behind the flyer plate. And this is the pressure. Okay. And for this 4 kilometer per second flyer plate, the pressure here is 300 atmospheres. That's not nothing. The velocity again is 4 kilometers per second. And I'm really struck by this temperature graph here. Okay, so what's happening is you're compressing the air here, and it's 5,000 Kelvin, and then this is your sonic boom, right? There was sort of a vacuum back here. The air from over here went in, and there was a two-sided collision, and it became 5,000 degrees here also. Okay, and I wasn't interested in this until somebody said, oh, the military is real interested in what happens behind a hypersonic missile, because if you know what happens to the air, you might be able to backtrack and find out where it came from. So I think we're going to start looking at that as well. But I have 2 specific things that I'm interested in. The first one's the raindrop. Okay, so I believe Tyler Takahashi is here also. He's in the audience. He spent the year developing a liquid droplet injector. And he's doing a summer at Sandia Livermore right now, but he'll be back to finish this up. And so what we're going to do is we're going to squirt a droplet of, let's say, water here. And it's moving at 10 meters per second, which is 0 compared to this thing. All right, so when it's right here, we'll shoot the flyer plate. And if it's water, let's talk for a minute about what happens if it's water. The first thing that happens is the droplet will break up when this shock wave hits it. And there are, I believe, 3 regimes for the droplet interacting with the gas shock. Okay, the first one is the low velocity entrainment regime, and that's just where you have a gentle wind and you blow the droplet around. The next one is the shock regime, and that's where you hit this thing at 300 atmospheres, and you create a shock wave in here, and the shock wave travels through here, and when it comes out, it causes jets, and the droplet breaks up, and literally nobody knows how this droplet breaks up in the shock wave, because no one's ever yet, I hope not, been able to do a single droplet experiment. Usually they just spray droplets, and then it's really hard to tell. Now, I gave a talk here a couple of years ago in this forum, and I talked about shocked water. Shocked water is nasty stuff. Okay, you know, you leave your bike out in the rain and it'll rust, okay? But if the water is compressed to a high pressure, it'll be really reactive. It'll be hot, it'll be compressed, and the pH goes way the heck up because, you know, the pH is like the H+ concentration. The water molecules tend to dissociate in the shock. So you end up with this really nasty stuff. And my colleague at Illinois is modeling this, but she doesn't even know what angle the water hits because we don't know the droplet. All right, so we're going to put water droplets. That's really good. The next thing that I want to do is I want to make a model for what's called the pulse detonation engine. Okay, so in your car, there's a spray of gasoline in the cylinder, and then there's from the fuel injector. In the old days, there was this thing called a spark plug, but now they do it differently. But what would happen is these liquid gasoline droplets would interact with the air, and they would burn and they would explode, and that would drive the piston, right? And that's what makes your car work. That's combustion, okay? So that's it's a combustion and an explosion. Nowadays, NASA and the Air Force are interested in what's called the pulse detonation engine. In the pulse detonation engine, you don't have droplets swimming in air. What you have is you have a high-speed flow of air hitting the droplets, and you create a shock wave, which does many things. First of all, it makes the explosion much more faster and powerful, and that's really good for spacecraft. And the reaction propagates much faster. Okay, so there are a lot of issues about what's going on in the pulse detonation engine. The way to study that we want to study that is this will be a fuel droplet, and there are lots of fuels you can use. Alcohol's one, hydrocarbons one. The spacecraft want to use liquid hydrogen. I'm not up for that yet, but maybe if I have enough success, we'll go there. But what I want to do is I want to see a fuel droplet explode. And actually what I really want to do, and Tyler has shown you can do this, is I want to put in 2 droplets a known distance apart, because it's the interaction between the shock waves from multiple droplets that create hotspots that cause the shock in the pulse detonation engine to propagate. All right, so one day I went, well, gee whiz, is this stuff really going to explode or not? And what I realized was that this would be in a different regime. I said the entrainment regime, that's where you just push the droplet. There's the shock regime where it breaks up. But now we're going to be in the ablation regime. In the ablation regime, I'm going to hit fuel molecules with air, oxygen-containing air, at 4 kilometers a second, and they're going to come flying off in a big explosion. Okay. And if you have 2 of these, there's going to be 2 huge shock explosions, and the modelers have not really been able to come to grips with that yet, so that's what we're after. So I wanted to know, is this going to happen? And I went, well, is there enough oxygen? Well, this is a 550, I said, if this is a 50 micron diameter droplet of, let's say, hexane, I can calculate how many oxygen molecules you need to oxidize it. And the oxygen molecules would be in this column here from the shock front back to the flyer plate. And I calculated there was a 250 excess of oxygen. Okay, so now I believe this is really going to open up a new field of extremely high speed collisions between liquids and gases. And it's hard to do, right? Because it's hard to accelerate a liquid to a high velocity. So I think with that, I'm going to just show you the most recent thing from Shivashri here, which is high-speed video of a flyer plate being launched in air and the shock wave. Okay, so this is the aluminum surface. You can see the length scale. Okay, and then when we shock it, we get, look, it looks really flat in the center. I told you that this thing is flat because we launch it from a flat laser beam. All right, but then, in the, we know it's flat in a vacuum. In the air, what happens is the air on the edges, right, it puts pressure here and no pressure there, so the flyer tends to curve. And I think we're going to have to go to stiffer flyers, but as time goes by, you see this bright light here, that's from the heat, that's from the hot gas. Okay, and then here you can see the shock wave. Here it is. All right, the whole idea is that the next thing we're going to do is put the liquid droplet there and see what happens. And you remember, right? You get this huge curved thing here from the air, right? And that's what we're seeing here. So this is my tabletop hypersonic wind tunnel. And I think it's very attractive for a number of things, because if you've ever seen a hypersonic wind tunnel, I saw one in Beijing. It's 3 football fields long. You have 1 football field full of compressed air, 1 football field full of your test aircraft, and 1 football field with a vacuum to catch the air. All right. So there are things obviously you can do with that. You can test whole aircraft, but my interest is always in seeing what's happening at the micro level, and I think we'll be able to do that. So I think that ends my talk, and I'd be happy to take questions if there are any.
Thanks very much for that presentation, Dana. Some really new and interesting things going on.
Yeah, I'm in the fun mode of my career now. The femtosecond lasers were good, but they weren't this much fun. Although I do have a friend that shoots femtosecond lasers in the atmosphere and makes lightning. It attracts lightning bolts. That's pretty fun.
Okay, are there any questions for Dana? You can either raise your hand, or you can type your question in the chat. I'd like to go back to your early in the talk, and you mentioned the fact that you wanted to control detonation to make it do specific things. Can you be a little more specific about specific things that you'd like to do?
Yeah. One thing I'd like to be able to do is turn it off and on. And you can do that by putting dense metal barriers in the detonation. Okay, and that's why it's important to understand the growth rate, okay? Because when you turn it off, you want to know if it's going to come back.
Yeah.
I want to make, or people want to make, micro detonation devices. There are a number of applications for these. One of them is if you have a really, if you're NVIDIA and you have one of these super duper AI chips, you don't want people taking it apart. And so you'd like it if somebody tries to take it apart, they will just self-destruct. You may remember Mission Impossible, right?
Of course.
Yeah, okay, right. So in 30 seconds, the message self-destructs. People scatter sensors on the ground to detect chemical agents, and they're just laying there on the ground. But if you suspect there's a chemical agent, you want to tell them to jump up like a little insect, and you can do that. Okay, well, so for micro devices, what happens is the physics of the detonation is very different. Okay, you don't do, I showed you there was that reaction zone, and I showed you that model, but anything that's smaller than that is very, very different. There's the shape charge, of course. There's what my colleague Nick Glumac did an experiment. One of the things you do is you take a bomb and you put it on a steel plate and you blow it up, and later, you go back in there and when dust clears and you see how big a pit was made in the steel, and you can go, oh yeah, this is a 2-inch deep explosive or a 1 centimeter deep explosive. And what Nick did was he did one experiment with 45 grams of HMX and he got a pit. And then he did another experiment that was modeled by my friend and collaborator, Scott Stewart, where they took 3 15-gram explosives and triggered them exactly the right way. And these three things, the three detonations cooperated. So each detonation was hit by 2 more detonations, and that's a big perturbation. And then there was 10 times more damage. All right. So those are some of the kinds of things that you need to understand the growth rate to control.
So when you do that, I mean, sort of technically, I guess, is the question, what do you need to do technically to exert that kind of control? I mean, in an actual device.
Well, there are 2 things actually, there's a lot of things you can do, but let me mention 2 of them. The first one is you can have 2 explosives interacting, right?
Sure.
So that's dynamic. Another one is that you can have an explosive suddenly enter another explosive, which is different. Or you can do what's called corner turning, okay, which is you have a small charge that goes into a big charge. And so the detonation of the small charge goes in there and suddenly it has to turn the corner. You can put tungsten balls or tungsten, you can put obstacles in there that give you complex, they're shock deflectors. Let's see, what else was I going to say? Oh, you can do multi-point initiation. You can take a big bomb and create a number of detonations at different places. Let's see, there were a couple other things. It'll come to me, but
Yeah.
oh, I know. You can shoot pulses of microwaves in. So you can have little pieces of aluminum in the bomb, and you can hit it with a microwave pulse, and the aluminum, don't put aluminum foil in your microwave, right? They'll get hot and start a reaction, okay? And so these are all, and you can also do it with sound, but microwaves right now seem to be the preferred way of external control. So there's internal control, internal dynamic, internal static, and external control.
Nice. Wow. Okay.
And then, I mean, the one rule is don't be there when it's happening.
Yeah, of course. You did mention general chemistry. I do have a general chemistry question that you give me an idea for a topic in thermochemistry here. So your enthalpy of detonation is given in kilojoules per cubic centimeter. Is that some kind of a specially determined enthalpy, or is that just the enthalpy of reaction scaled to the density of the material?
Okay, well, the first thing is, I don't have to lecture you on thermochemical tables, but those are generally for doing things reversibly, and this is an irreversible process.
Okay.
Right. So the heat the heat that's produced and the heat and work are different. Right. But if you remember, you probably remember that lecture, but you get the maximum work for reversible and the minimum heat. But
sure.
So number one is it's just empirical, right? And it depends on the size and shape of the bomb and all kinds of stuff like that. But so those numbers are a little fluky. Whether it's kilojoules per mole or kilojoules per cubic centimeter depends on where you're sitting. I think that really, I think what soldiers want is they want per cubic centimeter or per kilogram. Okay, and then it depends on whether you're weight limited or volume limited. Okay, so if you've got a bomb case, if there's a bomb casing on an A31 Warthog, and you want to put a new explosive in, right? You want to know how much energy you can get in that volume. Torpedoes, a lot of things are volume limited. In spacecraft, probably they're more weight limited. Okay, so right now I'm pretty focused on volume limited. That's why volume limited, there's more information in that than weight limited because there's also a density in there.
Okay. Yeah. Very cool. One thing you have talked about in the past has been spectroscopic measurements on during these processes. But so with the things you're talking about today, is that in the plans for you to sort of implement spectroscopic measurements to sort of track these reactions, or are they too fast?
No, they're not too fast, but they're happening at high pressure and temperature, and it's often very hard. You know, listen, I can do spectroscopy on that air shock front, no problemo.
Yeah,
Okay, and I can see excited oxygen molecules, gas phase molecules through their rho vibronic spectrum. All right, but if it's a condensed phase and high pressure and density, it's pretty hard. I worked on this for a while and kind of gave up on it. And the team at Los Alamos put a lot of time and money in it. And what happens is when you look at the spectrum, it's a big blob, and then as time goes, it kind of blobs around, and that's about it. But the one thing that I can do that we've done that I want to do is you can look at the aluminum atom emission. All right, so I can watch the aluminum burn up doing aluminum emits at just under 400 nanometers. So just, 394, I think it is. So there's a big peak there. And then the very first product out of aluminum is ALO. And it emits in the visible around 550 nanometers. So we've been able to see those things in low density. Well, we've been able to see ALO in low density regions, but you can see aluminum in a lot of places. Up at Argonne, which I know you guys use a lot, there is a station where they have shock tubes and bombs and stuff. That was pretty hard. The guys at APS didn't really want them to bring bombs in, but the DOE eventually, after a very brief 20-year period of arguing, they were allowed to do that. And then you can do X-ray Raman right? You can look at the inner core electrons of the various atoms. And that's really, they're not as sensitive to the temperature and pressure. So you can look at what the atoms are doing. Another thing that happens is most explosives have too much carbon. Okay, I mean, they never have enough oxygen. Okay, so what happens is when you blow them up, you get soot. You get some kind of burned up carbon, often with other things in it. And those things precipitate out. And people have been studying those up at Argonne with small angle X-ray scattering. So you can actually see the soot precipitating inside the bomb. But when it comes to actually going, oh, this hydrogen atom is going to go over and make this molecule and lose an electron, I think that only theory is that maybe in 30 years, but right now, the molecular dynamics guys and the guys who are doing time-dependent quantum simulations probably have the best opportunity to see the chemistry. But I think and as I said, I was in that for a while, but now I think I came to the conclusion that all I really want to know is how fast the energy is coming out and in what form.
Yeah. Right.
And then I've feel like I've made a lot more progress doing that than worrying about where each hydrogen atom is going. So we'll see what the ultimate outcome of the the sort of atomic chemical kinetics and chemical reaction mechanism model does for this field.
Yeah, that'll be interesting to see. Russ has a question. Great talk, Dana. The application to hypersonics is terrific. Can you say more about the simulations to get the pressure and temperature? I assume you're trying to validate the numbers.
Yeah, okay. As in anything, there's an escalating pyramid of complexity you can introduce. Okay, this was a master's degree project, and the student Shivashri used a CAN code. And so what the CAN code gives you is it gives you the steady state solution. And we know pretty much everything about, no, that's not true. We know an awful lot about shock waves in air. Right, and so the air is modeled pretty well. Now, the next step that we would take is that we're not in steady state. This is a transient, and that's much harder, and that's what homemade codes are about. My postdoc's husband is in this business, and one of the things that he says is that the thing that's really poorly understood is ionization and electrodynamics. All right, so you ionize a lot of these molecules, and you create real, it's a very complex plasma. And he's working on putting magnets in spacecraft to push the plasma away so the heat shields don't ablate as much. And they're just the kinds of codes I showed you are really not yet up to the accurate plasma dynamics. Okay, so there's right now I would say that molecular atomic, when I say molecular, it's O2 and N2, let's say. Dissociation is understood, I think, pretty well on longer time scales. After 100 collisions, let's say. After 2 collisions, that's another story. But the electron and ion dynamics, that is really pushing it, and that's where it gets really complicated. Right.
Great.
And then you can see that that's kind of a new area here, right? Gas shock liquid interaction and gas shock solid interaction. That's certainly where you're ablating, or you're hitting the solid and you're superheating small portions of it, right? That's more like my hot spots, right? That's also something that needs a lot of work.
Yeah. Well, it'd be interesting to see how this all develops with your work.
I'm pretty psyched. A lot of people from Aero and Astro have been beating on my door. Number one, it's new, and there's just a lot of things you can do with it. But number two is just a cost issue, right? Not just being able to do it on a tabletop 100 times a day is transformative. Although, like I said, there are scale effects, right? I can tell you what happens at a small scale, and then on the scale of an airplane or a missile, that's another story. But the people who model those things, when you ask them what the greatest uncertainties are, they're the kinds of things that I'm looking at here.
Yeah.
Like how does the liquid droplet break up, for instance, right?
Yeah.
What happens when a grain of sand hits at a solid hypersonic velocity? These things are things that are not, the kinds of things that are understood are, if I take a thing and shoot sand at it repeatedly, I can probably estimate how deep the pit will be. But looking at the fundamental mechanism, based on a real-time measurement, is a whole nother story.
Yeah. That's terrific. We're looking forward to the next few years of what you're doing down there.
Yes, thank you very much.
All right.
Oh, yeah, you still need to come down sometime.
Yeah, I'm going to make good on my threat to bother you for a few weeks one of these times.
I would say, though, my group is quite a bit smaller now than it was at its peak. I think at its peak it was 12, and now it's 4. And during the summer is not a good time because people go to conferences. So sometimes you go in my lab and there's 1 or 2 people in there, and it's not the same. But if you come in September or after that, that would be super.
I'll do that. All right. Well, if there's no other,
I don't have to tell you, there's a shuttle, right? You get in in the morning, you go down to Urbana from UIC, right? There's a shuttle. You go down in the morning, come back in the afternoon.
Perfect. Yeah. Well, if there's no other questions, then please everyone join me in thanking Dana for a terrific overview of some really new and exciting techniques that are being developed in his lab, and some great new science that's coming out of it. Oh, wait, we have another couple of questions. Sorry.
I think those are clapping, but.
Oh, okay.
And I think there are people whose paycheck comes from me.
I guess those hands went away. So yes, they were clapping. So yes, thank you, Dana, for a terrific talk, and we'll look forward to talking with you again soon.
All righty. Thank you, Steve.
Take care.